Guten Morgen miteinander, so sind wir Zweig. Sind sogar ein paar Leute da, ist gut. All right, well, welcome to this talk about heat maps, why security visualization is so hard. Right up front, a heat map is what you see here, just so everybody has seen that. Don't let my accent fool you. I might sound like an American, but I actually was born and raised here in Switzerland, moved to the Silicon Valley about 11 years ago, and now live in beautiful San Francisco. I've been doing data analysis, log analysis, and visualization for about the past 15 years of my career. I worked at all kinds of companies like ArcSight, Splunk, which you might have heard of. Started a company called Loggly at some point, and for the past 3 years been running around, starting my next company, which is called Pixel Cloud, and some of what we do, I'm showing you here as sort of the research that goes into that. Now, this is nothing new. You all know attacks have changed lately, motivations have changed. It's not just the script kiddies anymore that we have to worry about, but it's nation states, it's criminal organizations that make a real lot of money by hacking into our systems, by stealing information. But the one thing I want to highlight here on this slide is that why so much of security has failed in the detection realm is because we're trying to learn from past knowledge. We're building systems today that are relying on signatures or things that we know about the past, and we believe that they're going to happen again going forward. So looking at attacks, it's very unlikely that a really motivated attacker is going to break into your organization just the way he's going to break into the next organization. It's going to be very specific to your organization. So we need to build systems that scale better in terms of the different capabilities they have to detect these attacks and not just rely on past knowledge. So network-based intrusion detection systems are probably not the way that you find tomorrow's latest attack. If you look at some numbers, this is really frightening. I stole a bunch of these statistics from different research, and what really surprised me was from the Mandian report, where they showed that 33% of breaches at companies were detected internally, so they had some systems in place to actually detect the attacks, but 2/3 of all the attacks in the companies were somehow reported by outsiders, by external people. That might be through a threat feed or something like that, or someone calling in saying, hey, we get attacked by your machines, what's going on? That is really frightening. We're doing something wrong with cybersecurity if we can't even detect our own attacks internally. If you look at these other numbers, they're even worse. 229 days is the average that they found hackers to be in your systems already before they got detected. Imagine what you can do if you own a network for 230 days. There's a lot of stuff you can do. You can take your time. You don't have to rush into anything. And then an annual loss of $7.2 million. There's a lot of product that you can sell to a company if you want to start your own company to do that. So what I want to talk about today, I sort of have 3 goals that I want to achieve with the technology I want to show you, which is we want to find intruders and new attacks, stuff we don't know about. We have no idea how these guys got into our networks or what they're doing. I want to find exposures early, and I want to communicate my findings to other people. I don't want to just ship a terabyte of log files to you and say, here's the proof that things happen, and here is how it happened. So the approach that I'm taking is basically I'm saying, well, I'm taking a whole lot of data that I'm collecting from my network, from packet captures, proxies, antivirus, whatever you have, and I want to visualize that stuff to start finding interesting patterns. The problem is, this is going to be over a terabyte of data, and generally, if you throw it in some kind of visualization, you end up with something like this, which is a hairball. Now, if you actually generate a graph, it looks something like this. It is really hard to interpret this, if not impossible. So the first conclusion is already security visualization is hard. How do we generate a graph or some visualization of a terabyte of data that actually communicates something? Well, let's start at the basics. We can take different types of visualization to present our data. I have a whole bunch on this slide. We can start on the top left. You have a pie chart. I'm taking a firewall log, I'm breaking up the different event names here into different slices of the pie chart, and I don't see very much. I see a big red slice, like, oh, what does that mean? Okay, well, let's go on with the bar charts. Here I just use all my different event names that I see in my system, and I show sort of a distribution in a bar chart. Maybe I can see something in here. Maybe I see that there's some events showing up a lot and some others don't, and maybe the ones that don't show up that much might be interesting. But again, it's not that much information that I can actually convey here. Well, let's move on to the link graph. Here I have a whole bunch of relationships that I start seeing between different machines. But as I showed in the previous example, the hairball, if you take more than 1,000 nodes, this gets really messy. Well, I can move on. This is something called a tree map, which has the capability of actually putting a lot of information into one single visualization. But it's pretty hard to interpret and read all these different labels, and so maybe not the right visualization either. This here is something called a parallel coordinate graph, where this is the first graph in this selection here that actually has a capability of showing more than just 2 dimensions of the data. Here, we had sort of 1 dimension, 1 field, right? The action or the thing that happened on the firewall. Here I had all my event names. Here, you can have different fields on each of these axes. But also, if you look, this is already pretty messy. If I throw 1 million, 2 million events in here, it's actually going to get really hard to even render this thing in due time if you don't optimize nicely. So if you look at how much information is actually conveyed by each of these graphs, this one here might probably win. Well, I'm going to suggest we use something that is called a heat map. A heat map, and this is just a fancy way of presenting one, it's basically a matrix. If you ever studied any statistics or anything, this is pretty simple. You have columns, you have rows, and every value in here is basically you encode in a color. So you just have some kind of a color scale. Number 42 would fall somewhere here into this blue. And this is an example of one of these heat maps, how they could look. So how do we map data to a heat map? Well, we have the columns here, and usually what I do is I map time on here. So time goes from the left to the right into the future. That's going to be on all my heat maps. You could also put some other dimension on here, and then you end up with something more like a scatter plot. And then on my rows, I can use anything else. I can use my source IPs, I can use my port numbers, I could use URLs, and whatever you have. And then one of these ticks in here is basically the value that says, in this time frame, I saw this, whatever IP address in this case, this many times, and then encoded in a color. Does that make sense? Pretty straightforward. So let's take a log record and map this into here, right? So we have some kind of a sudo. Someone did a sudo su on a machine to become root. So the first thing we're going to do is, while we have this heat map here, we take the timestamp and find the time bin that it falls into. So which column are we going into? And what we're doing, not every timestamp has its own column in here, but we're binning things into buckets of, say, an hour. So this one here would go into the May 5th, 2300 hour, which is this slice here. The next one would be the midnight, this 1 a.m., and so on. So we're making bins. And then we take the user root here, which determines the row, and where it intersects, we apply some function. In this case, I just added 1 because I saw 1 more showing up there. I think this should be still pretty straightforward, although it's early in the morning. Yeah? Okay, good. All right, so why a heat map? The heat map actually scales really, really, really well. I can throw 1 billion records in here, although the information is getting more and more aggregated, or more and more coarse, if you want. It shows quite a lot of information, more than a bar chart, because I have multiple dimensions, I can count different things. And what is very interesting, I can actually use different measures for an individual data point. So what I showed you just before is I just added 1 whenever I saw another one there, right? So if I have another user root at that time, I just add 1, I keep adding 1 if I see in that time bin another one of the users. What I can also do is I can say, well, instead of just counting how many times did I see something, if I'm looking at network traffic, I can say, well, for this IP address, how much traffic did it actually send on the wire? And I just sum that up. So I sum up a third variable. Or what I can do is I can do a distinct count and say, well, if I have my users, I want to see how many different machines did they log into in a certain time frame. So if I do that for all my users, I suddenly see who's using a lot of different machines over time. I'll show you some examples of that. But the problem with the heat map is still, well, the information content is still limited. It's still better than the other visualizations, but it's still sort of limited because we aggregate very highly. We don't see all the detail underneath the data anymore. Well, here is an approach that can help you sort of eliminate some of the drawbacks of the heat maps. This is a process that Professor Ben Schneiderman at the University of Maryland came up with. Ben is also the inventor of the tree maps, if you've ever played with tree maps before. What he said is basically, look, if you're taking a data set, what you have to do is you can't just dive in and go into one of the details and look at something very specific unless you know what you're looking for. So you have to start with some kind of an overview first, and I'm using the heat map here as my overview. Then from the overview, you find something that looks interesting. You go and zoom in, and now I can use a graph that doesn't scale that well, like a link graph here, because I don't have that much information anymore. And then from here, I might zoom around, I might move around, I might look at different things, and then I see a certain area that I'm interested in, and then I go back to the details that I want to look at, the raw log record, to actually understand what exactly happened here. That's usually the workflow that you would go through to analyze a larger set of data. So again, the overview, I'm using these heat maps because they can pack millions of records into them. They also allow me to, inside of the heat map, I can already zoom in and basically reduce the data that I'm looking at. And it already starts showing me certain patterns in the data that might be interesting to look at. And by itself, the heat map might already reveal things that I'm interested in. But it's also a fantastic navigation tool to drill down into some other kind of visualization. And really no other visualization kind of possesses these capabilities. Now, in the next few slides, I'm going to still use the heat maps, and I want to show you that even something as simple as this heat map has a whole bunch of challenges when you're trying to implement a mapping of data to a heat map. There's all kinds of things you need to think about when you design it. And a heat map is still a pretty simple visualization. And what I'm trying to illustrate is that if you're trying to take something else, like a link graph, the questions that you have to ask yourself when you implement it are getting even worse. So let's look at some of the challenges with the heat maps. The first one is a pretty simple one. I'm showing you a pretty packed heat map here of a lot of data, and I have, let's say, 1,000 rows. Well, if I want to label these rows so that you actually know what they are, I can't draw a label next to it because I just don't have enough pixels. Because right now I'm mapping one row to one pixel. I haven't seen a font that's just 1 pixel high, right? I can't really label it. So what are you going to do in that case? Second is, well, maybe one solution instead of having labels might be have a mouse over. So when you're moving around in your heat map, it will actually show you something in that tooltip that shows up. Well, you can show different things. You can show, for example, the position, meaning I'm showing you what row I'm on, so the root user, and what time bin I'm in. That might be interesting. You could also say, well, but I want to show the raw records, the logs that are actually making up that data point. In that case, like, well, do you cache all of that on the client, which could potentially be megabytes of data, or even a gigabyte or something like that. It might be a lot of data. Or you can try to do a request. Whenever you hover over something, you actually do a request to the server and you bring that data back. But that might also be a little too compute intensive and too much data transmitted all the time. The next question is of sorting, and this is probably one of the key problems of heat maps, and we were just talking about that over coffee earlier. If you have, say, you're looking at user activity. Well, you could sort the users alphabetically. In the end, the alphabetical order of a username doesn't mean anything. Just because my name starts with an R and I'm after Nico, doesn't really mean that we should be sorted that way. Maybe we should be sorted the other way around, right? So alphabetically usually doesn't matter. Maybe we be sorted based on the values. We might want to see, well, if there's similarities in here, if two of these lines look similar, maybe I want to put them together so that I see groups of different users showing up in here. Well, the question then is, what algorithms are we using for that? And even worse, what's the distance metric that you're applying to this? distance metrics are becoming very interesting when you do data mining and you start do clustering, for example. How far away is one IP address from another? How far away is my user from somebody else's user? I might have different user accounts. I might have Ram, I might have Marty, I might have Raffi as a user account. Well, they should probably be very close together. But how does the system know? So I have to teach the system these kinds of things. And that can get really, really nasty. Here you see an example. This is a random order of my data. And what I did here is I applied a clustering algorithm with R, if anyone knows R. I basically just used the Heatmap command, and it actually lets you cluster things. But you see that there's a band of users, or here it's IP addresses, that belong together up here. But I also have one that looks very similar down here. So somehow the distance computation was done such that it somehow separates the data into two big buckets and then starts sorting those. So the algorithm behind this is not exactly what I wanted. I want to have these guys show up next to each other. So I would have to go in and start changing these kinds of things, which gets really gnarly and pretty complicated sometimes. The next challenge is overplotting. Now think about you have 10,000 different users, but you only have a screen with 1,000 rows or 1,000 pixels high. So now you have to map 10,000 into 1,000. You can do all kinds of things. You can just do a very simple sum. So basically, if you take 5 or 6 or 7 rows, you just map them on one row, and you basically just sum up all the values in here. That's one way, but that might not exactly show what you want to show. Maybe you want to preserve neighborhood properties, and you want to have sort of a function that you're putting over it, more of like a Gaussian curve or something like that, depending on what you want to show. Now, if you have this one heat map with 1,000 pixels, you encode 10,000 users, when you start zooming in, are you going to undo the zoom or the overplotting? How are you going to do that? Then, if you start making these heat maps interactive instead of just having a static picture like this, there are all kinds of other issues. The very first simple one is, well, the user probably chooses a time frame that he wants to visualize. Start time and an end time, and this is what I want to show. Now think about the case where I have 1,000 pixels horizontally, and I want to map 1,005 seconds onto it. So I would make 1.005 seconds per pixel. That's kind of weird if I map this out that way. So how do I do that? Well, maybe what you could do is the user just specifies the start time. The end time is automatically chosen by the number of pixels you have. So it's always an increment of 1,000 or something like that. Or maybe a fraction there of like 500 or something. That gets actually pretty interesting if you start implementing this kind of thing. Then when you zoom in, I'm selecting a certain frame here, and I zoom in. Well, if you just keep zooming in, your tiles get bigger and bigger, right? So in the end, I end up with this one big rectangle that I zoomed in. But maybe that was that overplot that I have 1,000 rows in there that are just aggregated into one. So I have to start undoing my overplot and potentially fetch new data from the server, which might get interesting if you have to do that. Then I talked briefly about color mapping. I showed you that blue color range that I mapped my values to. Well, there's all kinds of ways you can map your colors. What I was using was just one of these scales here, but you could also use something like this where you have more of a discrete sort of mapping of things that might be, this is a firewall block, this is a firewall pass, this might be something else. So I might want to map it to something more discrete. You have to figure that out. Maybe you want to have multiple anchors instead of just like a blue or a red scale. I might have something like a rainbow scheme here, for example. But then if someone sees a green, well, what value was that? Was that 500 and this is 1,000, or was that 400? Or that's getting hard to interpret, right? So you have to think hard about what color schemes you use. Then something else that we found very early on when we started generating these heat maps was that the distribution of your values is actually not very normal, or it's not even very even here. So if you look at sort of the frequency of your values showing up, you might have something where these values here show up much, much more. So this might be certain port numbers show up way, way more than others. Port 80, 443, 22, you might see all the time, or is this a port, I don't know, 1434 or something else that might show up barely ever? Now, if you visualize that, you might see something like this here, where there's one of these very bright bars showing up and the rest is fairly dark. Well, if I change my exposure, basically meaning that I'm moving around these curves a little bit in terms of the mapping to the data, then suddenly I might see different patterns. So suddenly this thing here shows up that I didn't really see before. So you have to be able to play with these exposure values a little bit. I will show you an example where this becomes much more clear later. Then one of the last issues that I will present you here in terms of challenges for heat maps is, say, I'm analyzing some data with like my IP addresses communicating, and I'm zooming in, and I find this one machine that seems to have an interesting pattern like this guy here. Well, now I have this sort of one-dimensional data that shows me over time this is the activity the machine had. But immediately I have other questions. I'm like, well, what other machines did it go to? What ports did it use? So I call this a pivot, where basically I want to tell the data, look, everything that has this destination address here, I want to now look at the sources. What sources were connecting to that thing? So then you can pivot to some other views here. I might want to do the same thing for the destination ports. Now, the last challenge here is sort of the backend you're using for something like this. And we could talk about big data for hours here. This is just my one slide on large data, as I decided to call it from now on. You have to think about what kind of large data backend you want to use for this stuff. There's all kinds of things. You have key value store like a MongoDB or Cassandra or HBase. You could use a search engine like Elasticsearch or Solr. You can use a graph database, depending if you have relationships in your data. You might want to have a graph database to compute centralities and betweenness or shortest path between different machines or something like that. You could just go for a plain old relational database that everybody understands, like something like MySQL, and I can guarantee you most of the time that's probably what you want to do. People are ditching these databases because if you're getting into larger scales and you have a lot of data, you have to start sharding. So you have to figure out on what machine in your cluster you're going to put the data into. How do you partition your data? That's the biggest problem with relational databases, why people move to NoSQL and all that kind of stuff. Often you can probably buy a big enough machine and throw everything onto one node, and MySQL is probably way less headache than anything else. But if you want to do it right, if you want to do these kinds of computations for heat maps, for example, you will need a columnar data store. And good luck finding something in the open source world that actually works pretty well. What you can try to do is using something like Impala or Shark, if you have heard of the Spark stack. Those are very interesting technologies to use here. I'm crossing out Hadoop and MapReduce here because just throwing a Hadoop cluster in there and running MapReduce jobs over your data to compute these heat maps is not the right thing to do. MapReduce is a great technology if you want to process a large amount of data, generally all of your data, with the same thing. You want to parse all your data or something like that, or you want to compute big aggregates over all of your data. Then you can start doing MapReduce. But if you're having ad hoc questions like, how many different usernames did I have in this system? Or in this time frame, show me all the different IP addresses showing up. Hadoop is the absolutely wrong technology for that. And we can talk more about that in the break if you want. Now, I'm motivating why heat maps are so great, but they also have their challenges, obviously. And one of the big challenges is obviously that you can't see relationships in them. And these graphs here are much better suited for that. So you see relationships between different machines here, how they're communicating, what ports they're using. So relationships are not well seen in heat maps. The other thing is, and I mentioned this a little bit earlier, these parallel coordinates, if you have multiple dimensions, in my heat map, I can maybe sort of map 3 dimensions or 3 data fields into there. But if I have more, 12, 15, I can't map that anymore. So I can try to use a parallel coordinate where basically every axis here is a data field. So my source IP addresses, my destination IPs, my destination ports, the number of bytes transmitted, and a line in here basically represents one log record. So this IP talked to this IP on this port, transmitted this much data. So you can start seeing certain patterns in here. Like here, you have one very, very long-lasting connection, and all the other connections were not that long. So why was there one outlier in here? So that's the kinds of things you could see in here. So I hope that you saw that heat maps are fairly simple to understand by themselves. There's a whole bunch of challenges when you actually start implementing this kind of thing. And then if you were to implement a link graph like this, what happens when you hover over a node? What happens if you select one? Does it select everything that's connected to it? How do you define patterns on there and things like that? It gets pretty complicated. All right, so thinking back a few slides, I showed you this process, right? We started with an overview, we zoom in, we get the details on demand. Well, what we're actually working on is something a little more advanced even. Even if you have a heat map, it's often not that easy to find a starting point. It might be really messy. Some of the screenshots you saw were just a big mess, right? Well, what you can try to do is you can try to use data mining, mainly clustering, to have the system compute areas in your data set that look similar. In this case here, what I did is I took a firewall log or network flows, and I was trying to show or trying to find, are there groups of machines that seem to behave similarly? And basically what you find here, there were a couple of clusters, these dark parts here, and the rest didn't really cluster well. So this might be all my web servers down here, and this might be all my mail servers. And seeing that now, I can start zooming in and sort of work from there and already reduce my data set by a lot. So it kind of helps me summarize or aggregate my data even more. So here's another one of these guys. These are called self-organizing maps, if you're interested in what it is. It's basically clustering based on a single dimension. And when we started doing this work, we're actually not quite happy with it yet. There's so many different challenges here. One of the biggest challenges is figuring out what are the features, what are the things you actually input into your algorithm. By default, you would take something like how many bytes have been transmitted between different machines. You might say, well, what ports were they communicating on? But what happens if you do this naively is, let's say your traffic in your network is 80% Facebook. It's pretty much every corporation today, probably 80% of the network traffic is Facebook, right? So if you throw that in here, guess what? Your self-organizing map here will learn the Facebook traffic. So it might start generating certain clusters, and this big one here is all the Facebook traffic. And then the other 20% of the map here will be designated to other things. That's generally not what I want. I want to kind of throw that traffic away and have it learn on the rest, because that's the really interesting part. So there's a lot of different challenges you will have if you try to implement something like this. All right. What I want to do now is I'm going to show you a whole bunch of examples, and it's kind of getting more complicated the further in we get. We're going to start with this one. What you see here is, again, over time, you have different users that were active on my systems. And here, the color is basically, the brighter it is, the more activity I saw from that one user at that time. Now, if you look at this, do you see anything interesting? Well, you can also read the text, if you can open your eyes that much in the morning. It looks kind of random, right? You have maybe some kind of a cluster here. If this is day, this might be 9 o'clock in the morning. You maybe have something here that might be midnight, but it's still sort of random. But if you look at the user, the fifth from the bottom, that Vincent guy, and sorry if anyone is called Vincent in here, there's no association, I don't know that person. But this guy here has a very light pattern over the entire period of time. And that looks completely different from all of the other patterns in here. Just visually, I have no idea what the data is behind this. I don't know what the users are. But just visually, this looks different from everything else. That might be absolutely benign. When I was working at Splunk, we actually graphed the check-in history for our source control server. And we looked at what times do developers commit. And we had this guy, Mitch. I think he's a robot, because his check-in history was pretty much flat. So at 4 in the morning, he checked in as much as he did at 4 in the afternoon. Maybe between 8 and 9 in the morning, he didn't check in that much. It's probably his time to sleep. But this could be absolutely okay. It could also be that someone is abusing this user as a service and runs some kind of a script or something that you might want to know about. Maybe it's something malicious. If you got lucky, you found something that is really bad here. Here's another example that I actually stole with permission from Ty. This is different users again. Over time, you see the login history, basically. So when did users log into the system? You see the blue ones here is actually the root user, which I already don't like. Why are people logging in remotely via root? It's probably not necessarily a good thing. But then you see these kinds of patterns. You see something like this here, which is probably some kind of a brute force scan across different usernames, where someone is just trying out things over time. But then the interesting challenge here was to figure out, well, are there any interesting patterns behind the scenes that we don't see here? You could now try to apply all kinds of data mining and complicated processing and whatnot to figure out, are there any interesting patterns in here? Do you have periodicity, like things that keep repeating in the same manner or something like that? But you can also take a couple analysts that have some intuition and say, well, let us try this. We think this might be happening here. And in fact, what happened here is that in Ty's organization, an analyst said, you know what? I wonder, if I look at traffic coming from Turkey or just from different countries, so he basically split up all of the traffic into where did the logins come from. And he generated a whole bunch of different same types of visualizations. And what he found is the top one here are all the logins coming, or the attempted logins coming from Turkey. And down here, the logins are coming from the US. What do you see? What do you notice? The blue one looks pretty similar? It seems to be that these are almost the same, right? Like visually, we could probably overlay them and they're almost the same. They might not be exactly the same. If you run an algorithm over this is not going to match up probably. But visually looking at this, it's like, you know, these are pretty darn same. Now, what turned out is that someone used some kind of an attack toolkit with predefined usernames, and they just ran it from different locations and scanned this organization here. So this is the same script running from different sources coming in. That was a pretty interesting revelation. This is another example I got from my Norwegian friends. Someone was running a firewall at home, and these two gentlemen here knew that this person was graphing their data in this kind of way. So what they did is they scanned in a way that their pictures started showing up. Now, here's another quick example. What I did here is I just take some sources or destinations here. So every single row here is a different destination in my network. And if I look at this, it's like, well, yeah, interesting. There seems to be a whole bunch of machines that were not active here. There might be some other things showing up in here. But really, let's see if I can find something else interesting. And what I did is, between these two slides, I'm changing the exposure level. So the graphs are the same, but I'm changing that exposure so that I see lower values better. And what you might notice is that this thing here shows up by just changing the exposures. And suddenly I have this sort of periodic behavior in here. Now that might be interesting. I want to zoom into that. So this is just a zoom in on it. And I see that there's this IP address here. I hope no one recognized that IP range. This is not real data. This is fake. What I did then is I'm pivoting now. So I had this one source here, or this one destination, and I want to see in the next slide what sources are connecting to it. And if you look at it, this looks really messy. Nothing really that I could see. I can't. I'm not sure if you can. But then what I'm saying is I'm going to change, or I'm going to use some data mining. I'm going to use some intelligent sorting of the rows and see whether I see a pattern. And in fact, I just resorted the rows, and I start seeing this staircase or this step pattern here. And this is exactly, if you overlay it, this is exactly what we saw before with that one destination had that kind of pattern, so that matches up pretty nicely here. So by just applying some analysis steps, I was able to find what was actually responsible for this kind of pattern. Now, the other thing that you can do now is like, well, okay, I now know there's a bunch of sources involved that are generating this pattern. What exactly is it? What I'm doing here is I'm using a parallel coordinate plot where you see these different sources here. We had one destination, right? That one that we zoomed in. And then I'm also showing the port number here. And you see there seem to be some interesting ports down here. There's a lot of traffic going to that. There's also some higher port numbers that are being used here. What you don't see is the exact scale, so you don't really know what this port number here is. So I should probably put labels on here. But what I did then is I kind of know, this is just for illustrative purposes here, we had this one destination. So I'm eliminating that. On this graph, I just have sources and destinations. And you can, for example, select one of the sources, and you see that it's going to this port number, and there's a bunch or a couple of port numbers down here also. So you can start investigating what exactly was this traffic, and it seemed to be some kind of a scan. If you notice that there's only one sort of line that crosses here. All the others are sort of nicely going over there. So there seems to be some kind of a scan going on between IPs that are almost sorted here, which is kind of interesting. Here's another example. What I'm doing here is I have my users here this time, again over time, and now one of these individual blocks here shows me how many different machines did someone log into. So for example, here the red ones, this one guy logged into a whole bunch of machines, let's say 10 in that time frame. If it's a darker value here, it might only be 1 or 2 machines. Now if you look at this, well, you might be able to see some things in here. If this is a day worth of data, so if this is like midnight and goes to the other midnight, you might see that there's sort of a boundary here and maybe here, which might be a work day, right, 9 to 5. So you seem to have some normal users in this network. So what we can do then is say, well, okay, this trick with this resorting my rows worked pretty well earlier where we found that those steps. Let's try that here. We're sorting based on the similarity of the rows, and okay, well now we have the ones that have a lot of activity on top here, and then it gets less and less down here. Not sure how much that tells me really. Well, what else could we do to potentially find some interesting patterns in here? Well, every user belongs to one or more groups or roles. So we could try to visualize the different roles or sort it by the roles. So here, there seem to be some pretty clear sort of separation showing up, right? I might have the very active guys here, that might be the top 5 until about here, that are pretty active. They don't seem to adhere to a 9 to 5 pattern. It seems to be shifted. Then I have sort of this big block here, and then something else starts down here that they seem to be more active over the entire period of time again. Now, if I actually show you what the roles are, you have administrators, right? They start later in the day. You have salespeople. You have development. They're a little more erratic over time. And here you might have finance people. They come in a little earlier in the morning. So that now starts showing some interesting things. For example, inside of sales, what is this guy? He looks like an administrator. Maybe again, that might be okay. Maybe I have a power salesperson in there that just uses a lot of different machines or something. Might also be someone that is doing something that's not really part of their role at work, and they shouldn't be really doing this. All right, last example. I took a firewall log, a whole bunch of rows, and one of the challenges in network flows and firewalls is that the cardinality of some of the fields is really high, meaning that if you look at the different fields that you have in your data, like source IPs and destination IPs, you might have a lot of them, potentially a few million showing up in a log file. Now, if I want to generate a heat map of all my sources, I have like, I don't know, 100,000 different ones hitting my network. How am I going to visualize that? That might be pretty hard. Well, how do we start an analysis? What I did here, I basically came up with some ideas that I had about the data set. And I said, you know what? I bet, or what I'm interested in is, if a machine, a source, comes into my network, and generally a machine should either be blocked because it's doing something stupid, or it should be allowed. because I really want them to access my web server, my mail server, whatever it is. But if a machine gets blocked and then passed, that might not be so cool, because maybe someone is trying to scan me and then gets in successfully. So I really want to see activity where I have blocks and passes afterwards. And what that helps me with this hypothesis, with this idea, I can actually pre-filter all of my data. I can throw everything away that was only passes, and I can throw everything away that was only blocks. And now I'm left with a data set that I might be able to work with that's a little smaller. Now, the other thing that I said is these low-frequency sources, so sources that I don't see that much and might get passed and blocked, I might not be interested that much. If they only show up 2 times in a log file over 2 months, it's probably okay. I mean, I might stretch it a little bit here, but I'm making this assumption for now. So what I'm going to do then is I'm using my heat maps again, and I have a very simple visual mapping. I'm saying, well, the sources, I'm going to put in my rows. Time, again, is going over here in the columns. And now my color mapping is a little different. The color mapping is such that if in a certain time frame, so in one of these time bins, let's say in an hour, if I only saw a pass, it was only led through my firewall, it's going to be green. If I only saw it blocked, it's going to be orange. And if I saw it both passed and blocked in the same time, it's going to be dark red. Okay? So now I said the low frequency ones, the ones that I don't see much on my firewall might not be interesting. Well, here is the ones that show up less than 10 times. So if you did the sum over a row, it would be less than 10. Here's my outbound traffic, and here's my inbound traffic. On the inbound traffic, I have something like 36,000 rows. And those who were around me, like either this morning or last night, I was trying to actually apply some data mining on this thing to sort it, like we did before with the arrangement of our heat maps. And I actually even put it on one of my servers and ran R. I think the process is still running from last night at like 10 o'clock. It's not done yet. So I'm probably just using the wrong algorithm to do this, because it shouldn't be that hard to sort 36,000 rows. If anyone knows R and knows seriation, please come see me. I need some help. But what we see here is it's really kind of random in here. Right? I can't really see any pattern. But on this one, I do see a pattern, which I kind of didn't expect. So let's quickly see what that is. So I have some outbound blocks. Traffic going out, it's blocked. And I did some command line widgery. Don't look at my regexes here, they're horrible. They were working quick, and it worked. But it basically, what I did is I took the sum of the columns in here and just summed up. So every time bin, I counted how many times these guys showed up. And I found that rule number 238 in my firewall log is actually spiking here over that period of time. And if we actually look at some of the log records that were behind this, it's kind of funky, and I'm still not sure what's going on here. But there seems to be basically the responses, so the server to the client is being blocked going out of my network. So it was not even the initial, it's not the incoming traffic, it's not the SYN that's being blocked, but it's outgoing traffic, and it's not even the SYN ACK, but it's some arbitrary ACK that's being blocked. Now, I have an idea. It might be that the firewall lost state at that point. Maybe it's a long-lasting connection and it dropped the state table or something. Otherwise, I really don't know what it is. What also is kind of suspicious is it's not that these show up 4 times in here, but that the source port is 1338, which is kind of a low port number. I would not expect that as a source port generally. So still not sure what it is, but this seems to be interesting to look further into. Now we go back to the high frequency stuff, right? Everything that showed up more than 10 times. I'm left with 672 rows, 672 sources. So that seems pretty interesting. I actually see a bunch of patterns in here, right? So the first thing I did is I split it up between inbound and outbound traffic. Outbound very nicely. Here's my IP address range internally. And then I had these 2 IP addresses in here. I have no idea what they are. I'm pretty sure this was a misconfiguration of a box sitting inside that was blocked going outbound, right? It was only blocked. And then probably someone here noticed, oh crap, we configured this guy wrong, changed the IP assignment on the machine, and then it was okay. It might actually be this guy here, right? Because that guy starts showing up from here on. I have no clue what this is. There's a machine in my network that has some weird IP address, try to go out every now and then, being blocked. But it's at least being blocked, so whoever administers this firewall probably did their job. There's a bunch of other stuff in here that I might find interesting. There seems to be this sort of break here, something happens there. There seems to be this kind of line we can draw through there. I have machines that stop being there, like this guy. Machines that have been blocked and passed up to here, and then they were only passed. There's an interesting pattern here. Suddenly this guy gets passed, then he goes away, and then he comes back and it's being passed all the time. So something going on here. What I did is I took this pattern and then generated a link graph. Sorry for the resolution, I was scaling things here. But basically, you see sort of these two things. The green stuff here, the passed things, are showing up in this graph here. So you have, it's just a node that says pass. It goes to all these destinations here on these different ports, so port 80, port 53, and echo replies. That's probably all right. And then the block part is this here, where I had a couple destinations here. These are multicast addresses on some weird ports, 5353 and 423. 423, you can go crazy trying to figure out what that is. It's bonjour on the max, where the machine is like, hello, hello, I want to talk to you, talk to me, talk to me. So fortunately, this was blocked at my firewall. I can keep going on here, right? We can look at the inbound traffic now, stuff coming in. I'm looking at only my top rows. I'm going to zoom into this pattern here that looks very interesting. And then I noticed that there's all kinds of stuff happening here, all kinds of blocks, and there seemed to be sort of this periodic behavior. What the hell is that? I also have this green line showing up here. Actually, this is one of the blocks here. Again, I think I wrote these firewall rules, and I hate myself at this point, because I seem to have written the rules on the ACKs, on the going out traffic instead of coming in. Because here, again, I block on an ACK, actually a SYNAC even, from port 80. So I'm not quite sure. I don't have my rules set anymore, so it's really hard to verify really what the underlying rules were that caused this kind of behavior. But that was interesting. And it turns out I have the same pattern here. These guys were all blocked. This guy was passed. And it was actually the same kind of traffic. It's all port 80 traffic. So it seems like this was actually one of the web servers that was being able to talk back out, or was allowed to be a web server. There's another pattern, it's the last one here, that I found interesting. There's really a lot going on. And what I did then is I generated this graph where you basically, this is the source, right, coming into my network. And I'm showing all the destinations it's going to and what port number it was actually using. If it's red, it was blocked. So my source, this guy coming to this machine, was on echo requests, was blocked. And there was this one guy on port 135 that was kept being blocked. The pings came through, but then it was blocked on 135, which is MS Blaster. But there was one node where it was actually passed as well. That's a little concerning. All right, with that, I'm actually out of time, but I think we saw that attackers are still very successful getting into our networks. We need to do something. The data generally has the information inside that could help us find the attackers. We have a big data problem in the end. We need some analytics and probably some visualization to find the interesting stuff. I hope I was able to show you that visualization is kind of hard, but I think it's worth trying it and playing with it. Play with some heat maps. And if you have any ideas for sort of cool heuristics or workflows for analyzing certain data sets, please come see me and let's geek out. Thank you.